All right, so I just wanted to go through the notes for the very, very first day of the very last unit in APChem. We're looking at the solutions unit, and we're going to be covering a few things together. This graph that is on the slide over here, you guys probably have recollection of seeing before in honors chem or general chem. And this is the heating curve of water. Okay, and you have a few things going on. You have time is passing as you go left to right here, so more time is passing. And as time increases, or as time goes by, your temperature is also increasing because heat is being added to water in this graph that you have over here. So there's a few portions of the graph that we have. You have three upward slopes here, and you could tell that it's referring to three different phases for H2O. You have H2O as ice here from -10 to 0 degrees Celsius. And then from 0 to 100 degrees, you have water. And then once you get to 100, you have steam here in three different parts. And as heat is being added, you could see the temperatures that are rising here, which should make sense because heat's being added. But you also have portions of the graph here where we have these flat plateaus. And anytime we have these flat plateaus, it's being referred to as a phase change. So here, once ice actually gets all the way up to 0 degrees Celsius, it starts to melt. Okay. Or if we're going the opposite direction, at 0 degrees, water would start to freeze. And then this phase change that you have going on over here, you have vaporization of the water, which is water turning into steam. Or if you were going the opposite direction, you would have steam turning into water. So that would be condensation here. So you could see that during our phase change, good thing to know is that the temperature doesn't actually change. So the temperature is going to stay constant throughout a phase change. But there is a rationale for this. Your chemical bonds are not being broken during a phase change, but your intermolecular forces are being disrupted here. So the reason why we have these plateaus like here for melting and here for the vaporization is that even though heat is still continually being added with time, all that energy is being used to actually disrupt up your intermolecular forces in the ice and also in the water so that it could turn to steam. So there's a few definitions that we want to take a look at here on the slide. Number 2, this is your heat effusion, which is what you guys had it referred to as last year, but we know that the H really here is the enthalpy. And basically what the heat effusion is it's the energy that you need to take something that exists as a solid, such as ice, right? And to take an entire mole of that solid substance and to convert it all the way over to a liquid substance. The AP test got rid of some of these calculations that we had to do for the heat effusion, but just as a reference point, the enthalpy of fusion is calculated by taking the mass of whatever your substance is and multiplying it by the latent heat of fusion, which is a constant. And for ice, that has been 80 cals per gram. Okay, so all this means is that to melt 1 gram of ice, it would take 80 calories of energy for that change to actually happen here. Okay. Now we also have melting point and we have boiling point, but these are a little bit different from your typical melting and boiling point just by the use of the word normal. And one commonality that you might have noticed in these definitions is the pressure at which the melting point and the boiling point are taking place here. So anytime you have a normal something like a normal melting point or a normal boiling point, the pressure under which the melting or boiling is taking place is going to be at normal conditions. So we have 1 atmosphere and 1 atmosphere for both. Okay, and we're going to be talking a lot more about vapor pressure later on, but it's when stuff starts to melt, basically when your solid and your liquid have the exact same vapor pressure. So the solid is able to go over into the liquid state, and stuff starts to boil when the vapor pressure of your liquid is at 1 atmosphere. And I wanted to explain what vapor pressure was through a really quick little drawing here. So if I had a beaker of water, and there are my water molecules here, okay, at equilibrium, what could happen is that some of these water molecules that are existing as a liquid, if they have enough energy, they could actually escape, and they turn into gaseous molecules of water, right? So it's still, this is water and that's still water, but it's just that the phase has changed. So these water molecules that exist as a liquid have escaped, and now they're up here existing as a gas. Now, vapor is gas, pretty much. So when we talk about vapor pressure, what's being done is you take a look at all these gaseous particles that are above the liquid or above the solid or above whatever it is you're looking at. And if you take the pressure of all these molecules, that is vapor pressure. And the reality is you end up with a dynamic equilibrium. So some of these molecules are leaving, they're escaping, but some of these molecules also come back down and they condense back down into water. So you have this continual motion of molecules that are leaving the liquid and molecules that are coming back down into the liquid. But once overall there isn't like a net change, then you would take a measure of that pressure, and that would be your vapor pressure right there. Supercooling, this is just a definition. Like it implies, it's the cooling of something, but it's supercooling. So it involves rapid cooling that's happening. And this rapid cooling actually causes something to actually exist below its regular melting point. The rationale or the reason why this happens is that the temperature change that occurs is very, very fast, and it doesn't give enough time for the molecules to actually go back to its original state, and then you end up getting crystallization happening here. And you guys might have seen little hand warmers or things that cool up really fast. And they kind of use this idea of supercooling and superheating here. And I'll give you guys an example of that next week on Monday when I come back. So superheating is just the opposite of supercooling. Again, it's involving a liquid, but this time we're rapidly heating it up. And if you are able to heat it up quickly, the liquid is actually able to exist as a liquid at temperatures above the normal boiling point, which isn't normal, right? Or not normal, but which isn't expected. So what happens when you have rapid heating is you end up getting a lot of really, really fast molecules that end up accumulating in one place. And you don't get enough of these molecules. So you actually don't start to form bubbles like you normally would for the boiling process. But when the bubbles do eventually form, they end up being very, very large. You end up getting something that kind of boils over here because the large size of the bubbles is something that you would typically see for something that is superheating. And I don't know if you guys have used boiling chips before, but sometimes boiling chips are added to a solution when you're trying to boil things so that you end up getting a little bit more of an even distribution of the heat. And you don't end up getting these huge bubbles that could spill over from your solution. So supercooling, superheating, to be honest, these are not very important definitions to know. You will not see a lot of questions with this on the AP test, but they're just on the solutions unit. All right, this phase diagram that you guys have over here, we I believe in your notes you have a huge space for it, but it's not actually drawn out. So if you want to take the time to pause the screencast really quickly to copy down a diagram like this, and you could go ahead and pause now. And I will go through and mark off some of the important parts about this phase diagram here. So important thing to look at here, this is taking place in a closed system, okay? Meaning it's not in an open system where you would have atmospheric pressure and everything else affecting it. We have three different phases that we have inside this graph. You have a solid, we have a liquid, and we have a gas, right? And on the y-axis, you have your pressure in atmospheres. On your x-axis, you have your temperature in Kelvin. This point right here, the triple point that we see in your notes, it exists when your solid and your liquid actually have the exact same identical vapor pressure. And in equilibrium, all three phases actually exist together. So if you were to know, or if you wanted to know what would be the pressure and the temperature that your solid, liquid, and gas all exist in one state, that right there would be your triple point. So you would check out what the atmosphere here would be and what the temperature here would be. Now, post 2014, the AP test actually got rid of phase diagrams exactly like this, and they got rid of terminology like the critical point. The triple point, I feel like, is just a really simple thing for you to be able to point out still, but you will not see a lot of questions directly pertaining to this graph on the AP test. But this graph does kind of help give an idea for phase changes, which are important to note. So let's just kind of use this as a tool to talk about the different phase changes that could occur from one phase to another. Okay, so we have these different arrows here, and let's just go through and label each one. From a solid turning into a liquid, this is just your plain old melting. From a liquid turning out to a solid, we have freezing. From a solid turning directly into a gas, like CO2, we have sublimation here. And from a liquid turning into a gas, that's vaporization. And then from a gas going back to a liquid, we would call that condensation. Quick thing to note here are all of the arrows that are pointing over to the right. These are going to be endothermic reactions because heat is needed to make them vaporize, melt, and go through sublimation. And the opposite processes, the ones that are going to the left, these are going to be your exothermic reactions where heat will be given off and things are getting cooler as this happens here. This is a little note here about sometimes people think that if you go outside and you're at a ski resort and you see snow and water vapor at one time, that is something that is referring to triple point, but your system isn't really closed and we're not really talking about something in equilibrium. So this would not constitute something for a closed system. These guys here, I think I took them out of your notes, and let me just double check. Yeah, that's not in your notes, so we're good with that. You don't need to know these definitions anymore. Critical temperature, critical pressure, critical point for the AP test. Okay, and I'm gonna go ahead and stop this, and we're gonna just finish off vapor pressure in another video.